Okay, welcome everyone to my continuation of what are my favorite theorems. As usually my favorite theorems, right? So take everything with a grain of salt, very biased point of view. Anyway, today I would like to talk about probably one of the greatest achievements in modern mathematics. I made a related video about one of the greatest achievements in modern mathematics, which was to write down kind of the periodic table, the classification of smooth symmetries, what I call smooth symmetries, so basically simple Lie algebras or simple Lie groups, because they kind of correspond to um, smooth symmetries, the symmetries of differential equations and so on. But finite groups, on the other hand, are more like discrete symmetries. And the related question with a much harder answer, a much more complicated answer, and a much more complicated proof would be the periodic table, so the discrete periodic table, the periodic table of finite simple groups. So I'm going to explain a little bit what the question is all about and how the answer looks like. I can't go into all details because the answer is quite complicated and the proof is really complicated. It's one of these monster proofs, which is probably still around 1,000 pages, between 1,000 pages and 10,000 pages in length. So it's really complicated. And it relies on the much easier classification of the smooth symmetries in a crucial way, as I'm going to explain. So in some sense, smoothness makes everything much nicer. So if you know Lie algebras or well, Lie groups, then the definition of them is much harder than the definition of a finite group. So a finite group is something you usually see maybe for the first time in the first class on linear algebra, maybe a bit later in the first class on abstract algebra. A lot of mathematicians, on the other hand, a lot of mathematicians actually don't know what really Lie groups or Lie algebras are, although they are very applicable in physics and so on. But the definition is just much more complicated, much subtler, much more involved. It needs more background. It needs the notion of a manifold, for example, for Lie groups. While for finite simple groups, you basically don't need to know anything. You can just get started. And that's maybe kind of the problem. So one of them, simple so groups describe symmetries, finite groups describe discrete symmetries. And there's just so much combinatorics going on that it gets a little bit out of hand. So in the end, the periodic table, which I'm going to show you in a second, the precise entries aren't that important. The crucial bit is that actually you can write it down. That's a bit surprising if you just think about how many potential counterexamples there could be out there. And not just that you can write it down, you can also prove that this list is complete. So here it is. So this is how it looks like. Don't look at it too closely. I'm going to explain a bit about it. But basically, it's built, well, I should credit Ivan Enders. So a link to his blog and a big PDF version of the periodic table where you can zoom in and see everything is in the description below. It's really awesome what he did. And it's a bit oversimplifying maybe, but still it's easy to remember, and that's the whole point. So this is basically how it works. Um, so you have the noble gases. So the noble gases are here. Uh, so the periodic table here is ordered like any periodic table. So groups are kind of, small groups are at the top, bigger groups are at the bottom, and you have some exceptional groups listed down here. But otherwise, things come in infinite families that you read off uh, following the, what is it, the columns, following the columns down. And basically what it says is the following. So you have those noble gases, and they are the cyclic groups of prime order. So C2, C3, C5, C7, C11, 13, and so on. So the cyclic groups of prime order. And on the other hand, well, you have the trivial group, of course, so this is this one here. And then you have the family of alternating groups, which I would like to think of as being groups of Lie type as well. I'm going a little bit into details later, but for now, just this sequence of alternating groups. So the quotient, well, the subgroups of the symmetric groups given by even permutations. And they start off a little bit late. Now, you might have heard about whatever the Abel-Ruffini theorem, saying that everything, basically A1, A2, A3, and A4 are solvable. So they aren't finite, they are not simple in particular. But from A5 onwards, so A5, A6, A7, whatever, up to AN, infinite family, they are simple. Okay. And all the others, all this bit, the rest here are in some sense um, finite groups, finite simple groups of so-called Lie type. And they arise by, I'm going to explain how this works or sketch how this works later, but they arise by looking at the simple Lie algebras or the simple Lie groups. So they arise by just knowing the smooth periodic table that I've talked about in a previous video. So the biggest bit here, so almost everything are those finite simple groups that you get from the smooth periodic table. You have the cyclic ones, which are, well, whatever. Well, the building groups, they're very easy. You have the alternating groups, of which you can think, as I said, also as finite groups of Lie type. So almost everything are finite groups of Lie type, and then you have 26 exceptions. So these are the exceptional group, of which you might have heard about the monster, which is the one right here, and its dimension, so its size is so big that you can't read it, but in the PDF you can zoom in and you can read the size. But what I would like to talk about today is not really about the exceptional groups. A lot of focus is on these exceptional groups. If you watch other YouTube videos or read articles about the periodic table of finite simple groups, I don't think that's the main point. I think the main point are, there are three main points. First of all, I think it's very surprising that the answer to this very innocent question is so simple, because the question actually isn't that innocent. If you think about it a little bit, it should be a very hard problem to classify discrete symmetries. And that the answer is not too bad is already very surprising. So that's part one. Also important is that you can prove it. That's part two. That I'm not going to talk about the proof at all, but the proof is really, really long and complicated, and has triggered a lot of new and interesting mathematics. So it's really important. And the third point, which I would like to make, is that basically everything, except a very small number of exceptions, namely 26, basically everything are groups of Lie type. So those Lie algebras, those underlying Lie algebras, they seem to be very important. They already give you the smooth symmetries, but they also give you the discrete symmetries in a very nice way. Also note that this is a classical classification in mathematics, in the sense that you get infinite families that arise very naturally, as I'm going to explain, and you get a handful of exceptions. And with a handful, I usually mean finitely many. Which again is a bit surprising, because a priori there could be infinitely many of those exceptional things, right? So these are the three main points. The table is much simpler. It is still complicated, but it's much simpler than you should expect it to be. You can actually prove what's going on, and the classification is the usual one, namely having infinite families which arise very naturally from Lie theory, from Lie groups, from Lie algebras, and some finite number of exceptions. Okay, so before we go into more details with the table, let me set up actually what is this all about. So in mathematics, very often you like to do classification problems. You have a notion that you really love, in this case, groups, and you ask, can I classify groups? Can you classify groups? That problem is just, I mean, this is completely bonkers. You can't. No, this is out of reach. No way. It's too complicated. So you would like to make it simpler. You would like to ask a simpler question. So instead of asking, can I classify groups, you would ask, can I classify elementary groups? And with elementary groups, people usually mean simple groups. They're really like the elements in chemistry, while groups itself are more like the chemical compounds, right? Everything you can build out of elements. And in what sense these are elements is you have some kind of Jordan-Hölder theorem, which tells you everything is built out of those simple elements. And the periodic table then should be kind of the classification of those elementary groups, which is a much easier problem than trying to classify all groups, because kind of the hidden complication is, okay, you can abstractly prove the Jordan-Hölder theorem so that everything is built out of those elementary parts, but it doesn't tell you if you have a group turning up in the wild, in real life, it doesn't tell you actually how that works. So kind of all the difficulty from the jump from groups to simple groups is kind of hidden in this abstract statement of the Jordan-Hölder theorem. In any case, you still have an easier question you would like to answer. Can I classify those simple components? And that's still a hopeless question, so you would like to simplify it even more. So for example, for the smooth periodic table, I showed you kind of to focus on simple Lie groups instead of arbitrary simple groups. Another thing you can do, and that's the topic for this video, is to study simple finite groups. So the emphasis is then on finite. Instead of arbitrary groups, you study finite groups. So arbitrary groups are really wild. So they're really complicated. So maybe finite groups will do the job. And yes, so the Jordan, and that's what you do, and you actually get an answer. As I said, it's a bit surprising that you get an answer, but you do get an answer to this problem. So let me say it again. So simple groups are groups without substructure. And substructure in the sense of groups would be, well, you first think it might be having a subgroup, but that's not quite what you do in group theory, because you want to take quotients. So you want to have a normal subgroup. So the simplest possible group in that sense are the groups without interesting normal subgroups. You always have the trivial normal subgroup, and you always have the group itself being a normal subgroup. You don't count that. And what remains would be to study those groups without other normal subgroups. And then there is this the theorem that I mentioned, the Jordan-Hölder theorem, which tells you that every group has such a normal sequence of normal subgroups, such that the successive quotients are simple groups, which means that everything is built out of simple groups, because Jordan-Hölder says a little bit more. They actually say this list of simple groups is unique up to renaming. Basically, and the composition series, that's what this thing is called, is unique up to reordering of factors, which is a really good statement. Like, yeah, a chemical compound, you might decompose it in different chemical ways into its elements, but as soon as you get there, the result is unique. That's basically what it's saying. And if you write down kind of examples, let's say for abelian groups, it's kind of always the prime factors of your abelian groups. So what are simple abelian groups is just what are simple abelian groups will be just Z mod PZ, for P being a prime, so the cyclic groups of prime order. And the way to see this is basically boils down to something like, so here you have Z mod 6. It has a normal subgroup Z mod 2. And that's a simple, and the quotient is Z mod 3. Or you can do it the other way around. You could say it has a subgroup Z mod 3 and the quotient is Z mod 2. So the sequences themselves are not unique, but the result in the end you get is unique. And that's kind of the statement of the Jordan-Hölder theorem. And another example, which is really, really crucial, is that the symmetric groups, you kind of would like to think that symmetric groups, they arise everywhere, permutation groups, right, card shuffling groups, they should be important here. And yes, they are. They basically give you already the first infinite family of simple groups. They're not quite simple themselves. You get the alternating group, and that one is simple as long as n is big enough. For small n, the law of small numbers, some coincidences happen and it won't be simple. But you just found, okay, so let me summarize. You just found, without too much effort, two families of simple groups, very naturally arising. In the abelian case, the prime factors, Z mod PZ, which is also, by the way, easy to see that they don't have any further normal subgroups. For alternating groups, it's a bit harder to see that they don't have any normal subgroups, but it's also not too bad. Anyway, so the second family arises from symmetric groups, and I would like to think of them as being symmetric groups, although strictly speaking, they are alternating groups. but they're basically symmetric groups. So you have a symmetric group, a very nice permutation group, right? So two nice families, cyclic groups and symmetric groups. And then you continue. Um, and this is well known for ages. And the last part of the classification was then done in kind of writing down this list was roughly done in the 50s by Chevalier and Steinbach. But it goes back to Lee himself, basically. So the idea is as follows. You have this list of simple Lie groups. So just take it. So take one of them, like SLN, and that's basically a simple Lie group, right? You have this list. You can take any of them. And usually they're defined over some infinite field, like let's say the complex numbers. Matrices, n by n matrices with determinant 1 over the complex numbers. But why do you need to take the complex numbers? You can replace your complex numbers by your favorite finite field, okay? And now you have a matrix algebra or a matrix group over a finite field, which means actually you have finitely many elements, right? It's just a counting problem. You can actually say how many elements. So if my field has q elements, then in this case, for example, SLN FQ would have, well, this number of elements. Okay, but it certainly still is a group. Like it was a group before. You can multiply matrices. You get again a matrix with determinant 1. So it's certainly a group. We have inverses. That's basically how it's built. And now you have a finite group. And that's almost the finite group you're looking for. You're almost done. This is almost your simple finite group. And you again get a list of simple finite groups by just taking your simple Lie group and plotting your finite field. It's not quite right. So it again has a center, which you need to get rid of. The center is usually something like identity minus identity. You get rid of the center, and you get a and you could play the same game with all the others. So let's have a look at the table more closely. Okay, we're back to the periodic table of finite simple groups. Now in the PDF version, which I said is linked below, so you can zoom in quite a lot. And this is how it works. I kind of want to ignore those here. So those are the exceptional groups, which I'm going to talk about a little bit later. But basically now you can zoom in or whatever. Okay, and you can read here. So maybe sometimes they have alternate names. There's certain symbols, there's certain order. For example, the monster is here and the order is still not readable because it's so huge. But anyway, so here's the list of the Hickman-Sims group, for example, HS of order 44,352,000, whatever, and all the others. And more interestingly, you have those infinite families here. So let me zoom out again. So those infinite families of the alternating groups, the cyclic groups, and groups of Lie type. So this is how you should read it. So you have a type A family coming from exactly the procedure I described before, or a variant of the procedure in general that I described before, by taking your simple Lie group associated to type A. You have a type B family, you have a type C family, you have a type D family. You have a type E family here, you have a type F family, you have a type G family. And then you can play around a little bit more. Instead of getting rid of the center, you can twist structures a little bit and you get all the others. So you have a type D2, type A2, so kind of basically a twisted version, something like that. And you have the same for G, F, B, E, and D ordered in a certain way. But the point is, all this big junk here in the middle, all of these infinitely many, these are all groups of Lie type. They are all obtained by taking your smooth symmetry and specialize it to a finite symmetry, which is pretty beautiful and a bit surprising. As I said, you need to massage things a little bit. You need to get rid of the center or whatever, but basically that's what's going on. And I really would recommend to look at this PDF, because now you could zoom in and you could look at, for example, the formulas for the dimensions, which is pretty awesome. So here is E6, simple group of E6, depends on Q. Q is the element, the parameter in my finite field. Remember FQ, and well, you can write it down. I can't even read it. So maybe you need to zoom in a bit more. this is a maximal zoom. Anyway, you can kind of read it. It's some expression in Q. And yeah, so this is a periodic table of finite simple groups. And I said again, because it's important, the biggest chunk of it is taking your simple Lie group and specialize to a finite field, massage the result a little bit, and you get your simple group of, you get your finite simple group. And you get, of course, infinitely many of them because you have already infinitely many starting configurations. Okay, and that's basically how you get the whole periodic table. And that was known, as I said, basically in the 50s or let's say 60s of the last century. And then the classification proof took a little bit of time. It's still kind of work in progress because people want to make it shorter, but kind of the accepted version of the proof appeared around 2000, 2005, something like that. So much later. Most of the groups at that point were already known for 100 years, 150 years, something like that. And that's then exactly the statement. The discrete periodic, so the point is that this periodic table is complete and non-redundant. So non-redundant is easy to see, but complete is non-redundant means you're not overcounting twice, and you have to be a bit careful with low numbers because there are some low number coincidences. But basically, that's not so hard. It's just bookkeeping. But that it's complete, that's the real meat. So that's really hard. That's kind of this proof that took a long time, and that's 1,000, 2,000 pages, whatever. And people are still trying to simplify it. And I say it again because the result is pretty easy and easy to remember in some sense. You have three infinite types of things, in some sense two. Let me explain. You have the cyclic groups of prime order, you have the alternating groups, and you have those groups of Lie type, which are all just obtained by specializing your smooth symmetry to a finite field and massaging it a little bit, get rid of the center, for example. And depending on how you count, you have 26 or 27 of those exotic examples, or those exceptional finite groups, which is kind of surprising. The only surprising thing is that you have a finite number of them. A priori, you could have an infinite number, but no, you have a finite number. But anyway, the point I want you to remember is that almost all of them can be constructed using Lie algebras and Lie groups, which should really tell you that this Lie theory developed by Lie, whatever, 150 years ago, that's really important. It's really a basic property of nature itself. So let me get this. And to make it even better, so I'm not quite sure how to fit in the cyclic groups, but you can kind of make those two again the same. So you can say that alternating groups are also of Lie type if you want, if you allow something like a field with one element. There's an article describing how this should work that I link in the description below. But basically, the alternating groups are also finite groups of Lie type. So almost everything except those noble gases, right? Those guys here, except almost everything is a finite group of Lie type. And that's a statement. Again, the real meat is the classification itself. But it's still easy to remember. Almost everything is a finite group of Lie type. So let me at least talk a little bit about the exotic examples. There are 26. This is basically the subgroup structure of them. Not quite. You're not allowed to have subgroups. So this is a subquotient structure. You have this big one at the top, the biggest one, and almost everything else is in some sense, a subquotient of it. So these are the 26. So here's, for example, Hickman Sims that I mentioned before is here. It's a successive subquotient of this is what is called the monster. It is interesting in the following sense. Well, you have a finite list, so just pick the biggest one. But there are other very interesting groups, namely those that on those lists, namely those that do not arise as a subquotient of the monster. Here's a Janko. So Janko is group number 4, Janko is group number 3, and there's another Janko is group number 1, and you have 3 others. And they are usually named after their discoverers. The description is, of course, in the the complete classification is of course in the description below. But the point about them is you don't really need to remember how that looks like, right? As a table, you just look it up. The point is they're interesting because they are kind of exotic symmetries, right? So there's some kind of coincidences going on in nature, and your symmetries that do not arise from those infinite families, and that's why they're interesting. Yeah, but anyway, so let me wrap up. So there's a lot of focus on those exotic symmetries because they're exotic. People like exotic things, but actually the real meat is the proof that everything is complete, and the real observation here, in some sense, is that everything except of let's say cyclic groups and of those 26 sporadic groups is a group of Lie type. Anyway, so that's it for today. I hope you enjoyed the video, and I of course hope to see you next time.